Welcome back to differential equations. In this video, we're going to be talking about integrating factors. Integrating factors are the first in what you're going to discover is a long series of stupid little tricks that we use in differential equations. Unlike calculus and many of the algebra topics that you've studied previously, there is no concise unifying theory for differential equations and how to solve them. Instead, what we have is a sequence of here's something that works, and maybe something in this direction will help us get towards something that works. I like to describe the elementary course in differential equations as a bag of tricks. We are looking for more tricks to throw in our bag and hope that we can find the right one when the time comes. The method of integrating factors is specifically used when you have the case of a first-order linear differential equation. So remember, first order means that it's going to have y prime of t, and it's going to have y of t. Now, y prime could have a coefficient. The coefficient is allowed to have t in it, but it is not allowed to have y or y prime in it. So we have some coefficient here I'll call a of t times y prime of t, and some other coefficient I'll call b of t being multiplied by y of t. We add those things together, and on the right-hand side, we get one more function. I'll call it c of t. The first thing I want you to notice on this equation is that it is not separable. You cannot get the y's on one side and the t's on the other, even if a, b, and c are constant, unless you have the situation where one or more of them is zero. So I'm going to specifically require that a of t is non-zero. If a of t is zero, then we have an algebraic equation on our hand. We can just rearrange and solve for y of t, and we don't have to do any differential equations at all. And again, b of t and c of t are not always zero. If b of t or c of t was always zero, then this would become a separable differential equation and we wouldn't need anything more challenging. All right, the first thing I'm going to do is decide that having A, B, and C is just too much of a mess. So let's do a little bit of division. Taking advantage of the fact that A of t cannot be zero, I can divide both sides of the equation by A of t. Creating some new functions, P of t and Q of t, and we can rewrite this as y prime of t plus P of t times y of t equals Q of t. All right, nothing really exciting happened there. Nothing interesting happened there. The only thing that I did was recognize that it could be easier to write the linear differential equation using two arbitrary functions instead of three arbitrary functions. That's the form we're always going to assume. We're always going to assume that y prime of t is by itself, y of t is on the same side of the equation as y prime of t. There is some coefficient on y of t, and there is some non-zero term on the other side. The rest of this process is going to look like magic. We're going to define an integrating factor. We're going to call it mu of t, right? We'll use the Greek letter mu, and we're going to define it by a differential equation. We want to insist that mu prime of t is equal to p of t times mu of t. Why do we want to do that? Well, because somebody at some point in the past figured out that if you do this, then the derivative with respect to t of mu of t times y of t, take the first times the derivative of the second, plus the derivative of the first times the second. Right? That's just the product rule for differentiation. Substitute in the definition of mu prime, and factor out the mu from both terms in that expression. And we realize that this derivative has the left-hand side of our original differential equation still sitting in it. And so from our differential equation, y prime of t plus p of t times y of t is just q of t. All right. This is why the integrating factor works. Because at this point, we have a differential equation which can be solved using the direct integration approach. If the derivative of this expression is equal to a known function, then the original expression is equal to the integral. And we've solved the problem. Before I go into an example, the first thing I want to stress is that this shouldn't make sense why we chose to do this or how we were inspired to do this. It should make sense once you understand what the first step is. The rest of the process follows quite naturally. If you want to go through and work out each of these steps every time, you are welcome to. Typically, what you see in a course in differential equations is we have this. And I'll show you that we can go through and solve this using separation of variables. This is a separable differential equation in mu. So we should be able to figure out what mu is without too much difficulty. And in fact, some people just memorize this is the form, it involves an integral, but you can just write it down and you can go from there. Once you have that, you can substitute that in. You can go through this whole process if you want. Most people either remember this step or this step. I find that this step is easier for me to remember, so that's what I go with. And we can just jump in there. We have a process, it always works. Just like when you are looking at solving a quadratic equation in algebra, you go through, you do some work, factoring in this case, and then you are left with two equations, each of which are linear and easier to work with. The method of integrating factors takes a differential equation, which is not very pleasant, and simplifies it into two differential equations, each of which are quite a bit easier to deal with. That's where the power of integrating factors comes in. That's going to be something that we're looking for throughout, and we're going to hope that we can find it in many different places. I will give you a preview of things to come. It turns out that if you have a specifically kind of simplified differential equation, you can make your life even easier than that. But for right now, this is a great step in the right direction. All right, so let's look at a specific example. Let's see if we can make sense of this process. Again, we can do a whole bunch of diving in. But we'll start off with the differential equation y prime plus 3y equals 5. As linear differential equations goes, this one is pretty straightforward. We have some constant coefficients going on. Constant coefficients really make our lives easier. But remember that mu prime is mu times p, and in this case, p is just 3. So that means that mu prime over mu is equal to 3, which is, again, usually what I remember. Mu prime over mu is 3, or maybe the integral of d mu over mu is equal to the integral of 3 dt, where the natural log of the absolute value of mu is equal to 3t plus some arbitrary constant c. And we've seen this many, many times already. We know that this is going to turn into mu itself is equal to some constant a times e to the 3t. All right, there is our family of solutions to the first of the differential equations that we are looking at. Again, you can memorize anywhere in this process. Some people just have done this in general. Instead of putting a 3 there, putting a p of x, and you get that mu is going to be some constant a times e raised to the integral of p of x. I'm sorry, I'm doing t here. I should be consistent. P of t dt. All right, wherever you want to jump in, wherever you are comfortable jumping in will always work out. The process always looks very similar, although the actual performing of the integral can get to be a little bit uglier from here if we're not careful. The other thing you probably noticed is that I didn't put an a in front when I wrote that general form out. That's because on the next step, we actually don't need the arbitrariness. We need to pick any one function from this family. Any one will work. all of them will work. So we pick the one that is most convenient to work with. And the one that's most convenient to work with is the one where a is equal to 1. If we picked a different value of a, we would get the exact same solution. It wouldn't change anything at all. But picking a equals 1 is going to make our lives a little bit easier. Now remember from what I did before, d dt of mu times y must be equal to mu times q, the right-hand side of the original differential equation. And if I scroll back up, the right-hand side of the original differential equation is 5. So the derivative of mu times y is 5 times mu. Plugging in, mu is e to the 3t. And then solving by a method of direct integration. Right. Generally, if I'm in front of a class at this point, somebody in the class is trying to put that a in anyway and do this in general instead of picking the particular value of a for the function mu. And at this point, you can divide both sides of the equation by a. They're going to cancel each other out. Right? If we had included it in, there would be an a right here. There would be an a right here, which means there's be an a here and an a here that you could bring outside of the integral. So that extra a doesn't do anything at all. Even if you try to include it, it doesn't change anything. So there's more justification that we can just pick a equals 1 if that's the way that you wanted to approach this. In any event, the integral of 5e to the 3t well, that constant 5 is just a constant. The integral of e to the x is e to the x. And to deal with the fact that it's the integral of e to the 3t, we're going to have to multiply by or divide by that coefficient of 3. So we're going to end up with 5 times 1/3 times e to the 3t plus some arbitrary constant c. Now, to get y by itself, all I have to do is divide both sides of the equation by e to the 3t. And usually I would skip a little bit of the writing here, but I think for this particular problem, it's worth seeing at least once. When we go through and deal with the arbitrary constant, very often we have to multiply it or divide it by a particular constant, or even multiply two arbitrary constants together. And when we do that, it doesn't affect the constant at all. But in this problem, that's not quite where we're going to go because we're dividing by a function. And because we're dividing by a function, it has to stay there. Five-thirds e to the 3t divided by e to the 3t. Well, the exponentials cancel each other out and you're left with 5/3. But then you have 1 over e to the 3t times the arbitrary constant c. And one last step to clean this up. Remember that 1 over an exponential is the same exponential with a negative exponent. E to the negative 3t is the same thing as 1 over e to the 3t, and that gives us our general solution to this differential equation. If we had an initial condition, we could continue onward to figure out what the value of c is supposed to be. We don't have that in this case. I want to go through one more example to show you how quickly things can get out of hand in this situation. So let's take a look at another differential equation. Y prime equals 7y plus 2t. That doesn't look too complicated. I've introduced a variable t into the process, but I can very quickly rearrange this, and we can see that it is a first-order linear differential equation. So we should be able to solve it by method of integrating factor. Let mu prime equal minus 7 times mu. Solve from there, we'll get that mu, that's not a mu. Mu is some constant times e to the minus 7t. All right, I'm not going through and solving the separable differential equation. At this point, I think you've seen enough that you can do it on your own, but I do encourage you to pause the video and work through solving that on your own. Or again, in this situation of a separable differential equation with a constant coefficient, memorizing that this is what the solution is going to look like is not necessarily a bad thing. But regardless, once we have our integrating factor, we can continue onward from there, and we will get that d dt of y times mu, so y e to the minus 7t, is equal to the right-hand side, 2t times the same mu, e to the minus 7t. Right? Again, memorizing these steps or having them written down in front of you is not a bad thing because they look identical every single time. You don't have to go through and do them. If you want to, there is nothing wrong with it, but you don't have to. Then from there, we integrate both sides to get y by itself, or at least to get y out of the derivative for now. And then we realize that, well, actually doing that integral is going to be a little bit messy. When you have an exponential function being multiplied by a power function or a polynomial function, the tool of choice is generally to integrate by parts. Right, so we'll pick u equal to the polynomial factor 2t and dv equal to the rest of it, e to the minus 7t dt. Differentiate u to get that du is 2 dt. Integrate dv to get that v is negative 1/7 e to the minus 7t. And then this thing is going to turn into u times v, which is negative 2/7 t e to the minus 7t minus the integral of v du. Well, there's a minus there already, so that's going to be plus 2/7 e to the minus 7t dt. And at least this time we have an integral that works out nicely. You're going to get negative 1/7 e to the minus 1/7 t. You're going to get an arbitrary constant added in. So the negative 2/7 t e to the minus 7t hangs along. We're going to take that 2/7, we're going to multiply by negative 1/7, which is going to give me negative 2/49 e to the minus 7t, and then we're going to have plus some arbitrary constant. And on the left-hand side, of course, we still have y times e to the minus 7t. So to get y by itself, I'm going to divide each side of the equation by e to the minus 7t. And dividing by e to the minus 7t is the same thing as multiplying by e to the positive 7t. And that gives us our general solution for that differential equation. All right, so here's one I would like you to take a little bit of time playing around with. I'd like you to find the general solution of the first order linear ordinary differential equation y prime minus 1 is equal to 5y. All right, take a couple of minutes, play around with that, see where you can get to on it, and I'll see you in the next video.